All right, so the deal is that we just finished up a unit on equilibrium, and we talked about acids and bases. Now we need to talk about titrations and buffer chemistry. And the most complicated part of this is the buffer portion, which is why you guys had the POGL yesterday, because I figured that if you struggled with it just a little bit, you might be able to understand it a little bit better today when we talk about it. That being said, if you haven't gotten out your POGL already, one of the things I told you had to do for homework was get out the POGL, was do the POGL extension questions. Now, the POGL extension questions for number 17 asked you if you could essentially use the buffer indefinitely. And the answer to that question is no, you cannot use the buffer indefinitely, because at some point you're going to use up either all of the acid or all of the base or whatever. So so you just can't do it indefinitely. Now, the other thing that you should bear in mind is the fact that the higher the molarity of the buffer solutions or the weak acid and the conjugate base that get added, the more buffering the system can do. Does that make sense? Yeah? Next. These are the answers to 18, C, E, and F. Now, I have created a very special slide in an attempt to deal with this. But first of all, hopefully you guys identified the fact that this is clearly not going to be a buffer, in large part because it is a conjugate, a strong acid being mixed with a strong base, so that will not be a buffer. Now, the thing that I'm gonna focus on here are these two guys, are B and E. So let me get to the next slide and let me show you why one of those is a buffer and one of those is not a buffer, and it's kind of important. This C works because we have a strong acid that is going to be the limiting reactant compared to the weak conjugate base. And E works because we have a strong base because it's the limiting reactant when compared with the weak acid. And F works because we have the acetic acid being mixed with a strong base again, and this time the strong base is again the limiting reactant. So do you see how B and E are different, and D and, nope, I lied. So, does that make more sense though about about the query that some of you were having yesterday? Yes, no? Okay. So, here's the thing. On the left-hand side, this is solution B, and on the right-hand side, this is solution E. So I'm going to focus on solution B first. When you take equal concentrations of a weak acid and a strong base, they both get used up, and you only are left with the conjugate base at equilibrium. Okay? But if you take differing concentrations of the weak acid and the strong base, then what ends up happening is as long as in this situation, the strong base is the limiting reactant, then you do end up producing a specific amount of the conjugate base and a specific amount of the weak acid, and that creates your buffer. So the rule of thumb is when you're trying to identify whether or not whether or not a system is going to be a buffer, you have to take into consideration what's being mixed with what, number one, and what the concentrations are, or at least the volumes in this case. So the strong acid or base has to be the limiting reactant in order for a buffer system like this to work. So if I go extension question number 19 said the buffer system, or was asking if you dump the buffer, or if you compared the buffer pH to the pH of just the weak acid in pure water, what will happen to the pH? And the answer is the buffer system would have a higher pH, that is, be less acidic than the weak acid in water. The reason for that is the common ion from the salt shifts the reaction to the left, and it reduces the concentration of the H3O plus ions, which is usually the measure of a pH. Does that make sense? Yes, no? Okay. Question 20 asked about the the blood system pH or buffer system. And so it talked about asking you if you added some acid to the above buffer system, what would neutralize the acid? In this case, the bicarbonate ion would neutralize the acid. And if you added some base to the pH system or to the buffer system above, what would neutralize the base? So the carbonic acid would neutralize the excess base and bring you back to the pH of the buffer. So how does that feel in terms of the POGO? Better-ish? A little better-ish? All right, we'll take a little better-ish. All right, so here are your notes. As you learned in the POGO over the course of the last 2 days, a buffer is a solution of a weak acid and its conjugate base, or a weak base and its conjugate acid. Here is the buffer system that we're going to use a lot in the notes because I don't know why. Oh, I know why. Because acetic acid is basically vinegar, and vinegar is readily available. So if you wanted to make a buffer at home for your own purposes, you could just go grab some vinegar off the shelf and what?
For your own purposes.
I don't know. Yes, sir.
What type of vinegar?
Any vinegar.
Apple vinegar?
Well, I guess the you want to, yeah, the white vinegar would be better because it's just been diluted with water, whereas the apple vinegar is actually distilled from the apple process. They actually make alcohol with it and then they let it turn to vinegar. So it's apple vinegar is essentially hard cider that's turned bad.
Oh, that's fun.
Yeah. What now?
No, not in a weird way. I said my mom takes shots of
Apple cider vinegar because it's good for you.
Yeah, if you
yeah,
take one
well,
shot
it's
before you
supposed
go
to
to
burn your
bed.
stomach fat. She told me.
Yeah,
take
it
one
helps,
shot
it
before
helps,
you go to
it
bed,
helps
it's
you not
good
eat
for
as
you.
much.
She takes it in the morning.
Anywho,
Tastes good.
Anywho, the buffer here, we have the acetic acid being the weak acid and the acetate ion being the conjugate base. So that's the buffer system that we're going to look at. However, the exact same buffer can be written in the reverse perspective, in which case we have acetate ion hydrolyzing with water to produce the acetic acid. Regardless of how it's written, it's still going to do the same thing. So far, so good?
Yes.
Okay. Here's another example of a buffer. Here we have carbonic acid, which is a weak acid, being hydrolyzed with water to produce the bicarbonate ion. This looks very, very similar to the one that's in our blood. Oh yeah, that's because it is the one that's in our blood, and it keeps our pH somewhere between 7.3 and 7.4, okay? Ish. Now, if I go one step further and I take the bicarbonate ion and I treat it as a base because this is a polyprotic acid, I then produce a different buffer system, in which case the bicarbonate ion acts as the weak acid and the carbonate ion acts as the conjugate base. The issue with this is that if you note the pKa's are significantly different for the weak acids, and as a result of that, the pHs are significantly different. So if you got yourself in a blood plasma situation where you were heavy in the bicarbonate ion, and you didn't have enough carbonic acid, you would go into this basic system, and you would basically become pretty alkaline, and that's not good for you. So
That might be a health risk.
the conjugates, remember the one thing that you have to understand, the conjugates differ only by one proton, which is why the carbonic acid and the carbonate ion cannot be conjugate base pairs. So we go with that. So far so good? We're rolling. The common ion effect, which we learned about last unit or the unit before or whatever time we learned about it, is when a weak acid or a weak base and its strong electrolyte share a common ion, and as a result of that, the weak acid or the weak base ionizes less in solution. What that's saying is that by adding the strong electrolyte, the ionic compound, so like if we're talking about so that would be acetic acid, and we add something like sodium acetate. Adding this ion makes the weak acid ionize less in solution. And as a result of that, the common ion effect brings us back to Le Chatelier's principle, which hint, hint, wink, wink, nudge, nudge, if you've got nothing on the AP exam, like nothing at all, write something about Le Chatelier's principle. The worst they can, I mean, if you've already got nothing and you're getting 0, what's the worst that can happen?
Or molecular collision.
Oh, yeah, or molecular collision theory.
Those two babies are the mice,
All right, now, example number 1 says, and this is a very, very similar style question than the ones that we've been doing, that we did all last unit. So this one won't take us very long to get through, but we're gonna write the reaction here. So we're gonna have acetic acid being added to enough water to make 1 liter of solution. So this is our reaction. So I'm gonna have my acetic acid, which is going to be CH3COOH plus water. It's going to be hydrolyzed to produce the acetate ion, CH3COO minus, and the hydronium, or in this case, H plus. Okay? So initially, we have 0.3 moles of acetic acid and enough water to make 1 liter solution. So because it's in 1 liter solution, I'm just going to use moles because it might be easier to follow. So 0.30 moles here. Water is not significant because it's a liquid. And then at the beginning, initially, I have 0 moles of acetate ion and 0 moles of the hydrogen, the hydronium. And then in my C section here, I'm going to be taking X amount of the moles away, adding X amount of the moles, adding X amount of the moles, and then in my N section, I have 0.30 moles minus X, X, and X. So if I write my Ka expression, CH3COO minus the acetate ion times the hydrogen ion over the acetic acid, this will equal a value of 1.8 times 10 to the minus 5, which will equal X concentration, and 0.30 moles minus X concentration. So when I go through and I solve for X here, I get a value for X to be somewhere in the ballpark of 0.0023, which would be equal to the H plus. So I'm going to take the pH is equal to the negative log of the H plus, which will get me to the pH being equal to the negative log of 0.0023, which will give me a fun size pH of 2.64, which is pretty acidic. Yeah, like those candies. The smaller ones are fun sized, right?
Yeah. I've just never heard anyone use that term for things other than candy.
You don't have a short friend?
I mean, I do, but I don't call them fun size.
No, but a lot of times the short people will say, "I'm not blah, I'm fun sized." You ever seen that?
Yeah,
Oh, okay, all right.
I know what you're talking.
That's exactly how it sounds too. All right, so
Is that the orange up there?
yeah, it's the annoying orange. You don't have to worry about it.
Why are they just letting an orange rot in the chemistry room?
I'm not letting it rot.
Did your filter put that orange up there? No, it's probably Neil and Steven.
So hypothetically, if someone were to take the orange,
What else?
I would win
You would what?
the battle of wills.
so
Oh, it's who's.
so like I took the orange,
Right.
you would win,
Yes.
and the nasty orange would be out of the basket.
Yes.
I don't see a downside to that.
I would recommend doing that, exactly.
Can I go on?
But
We need
kind of
to
like
positive
this.
it.
But yeah.
And
What is this?
did I go too fast?
What's going on? We don't wanna know what's going on.
All right. So
Tell us, I'll have to ask the other.
He'll never
Here's the
tell us
thing.
how he hates Oklahoma.
here's the thing. In this system, it's a little bit different. This system is a little bit different than the last one. In this case, we are adding sodium acetate. So when I write the reaction, I still have the acetic acid being hydrolyzed to produce the acetate ion and the hydrogen, but the issue is that we still are starting with the same amount of acetic acid, so this is gonna be initially 0.30 moles. Water, again, is liquid, so it doesn't count, but we are also adding the 0.3 moles of sodium acetate, which, as you may recall, is going to make Na plus and CH3COO minus. So I'm adding more of that, so that tells me I'm going to be adding 0.30 moles of that and 0 H plus.
This changes everything.
What now?
So this changes everything.
Kind of. So now I'm going to be subtracting X, and I'm going to be adding X, and I'm going to be adding X. And then when I get down to the end portion, or the equilibrium portion, I'm going to have 0.30 moles minus X. I'm going to have 0.30 moles plus X, and then I'm just going to have some X. So when I write my Ka expression, same thing as before. Minus 5. I'm going to now have on top 0.30 moles plus X, X, and 0.30 moles minus X. So, as we talked about yesterday or the day before or whatever day it was, we are going to once again assume that X is too small to be significant or less than 5%. So we assume that that's gone, and as a result of that, 0.3 divided by 0.3 is 1. So that gives me my value for X to be 1.8 times 10 to the minus 5. Now, which would be moles. So because this is still in 1 liter of solution, that's actually going to be the molarity of the H plus. So when I calculate the pH here, which will be the negative log of the H plus, which gives me the pH, which will be negative log of 1.8 times 10 to the minus 5, which gives me a value for my pH this time to be significantly higher, 4.74, which is going to validate the statement or the question from the POGL that asked you what would happen to the pH of how could you compare the pH of a buffer with the pH of a weak acid in water. Example number 1 is a weak acid in water. Example number 2 is the buffer system of that weak acid. It's like I planned it.
Yeah.
That's crazy.
Weird. All right.
And that's it? That's all I have to do? Free time?
Yeah.
Moving forward,
No homework?
There's a lot of homework.
Oh, great.
How much homework do we have? Do we have a lot?
Well, to be fair, if it's a buffer and
We're not gonna
it
do
asks
all
for the
these notes.
pH,
can I go?
Yeah.
Is it
Yeah.
7.1, 7.2, 7.3, 7.4?
So, conceptually speaking,
hit the first, like, 10.
we're going to make the understanding that there are equal concentrations of the acetic acid and the acetate ion in this mixture, so their concentrations are the same. What should happen to the above equilibrium in terms of me adding more CH3COOH?
It shifts to the right.
It should shift to the right. Okay, why?
Because of the Shelly.
Yeah, but why?
It's okay.
Because if you add more acetic acid, it reacts with the water and creates more of the ions.
Right? You agree with that or no?
Sure.
What is that going to really react with?
I don't know.
You're adding acid. What's going to neutralize it?
Oh, base.
So Okay. Now, what if neutral,
Will.
will,
Will, okay.
I'll make that prettier. Because if you can't read it. All right, what about we add more acetate ion? What's it gonna do? It'll shift to the left. Why?
Because it will react with the acid and be neutralized.
Neutralized by the weak acid. Now, what if we add hydrochloric acid? So we're adding a strong acid to this buffer system.
It will be neutralized by the base
So which direction is it gonna go?
to the left.
Agreed.
Why is it going to the left?
Because it'll react with the base, which is
What base?
on the CH3Cl minus.
So it's gonna react with the conjugate base, yeah. Okay? Now what about if I add the NaOH?
It'll react with the weak acid and the reaction with the right.
Okay, so how does that feel inside your head? We okay? Weak acid, conjugate base. So we have, again, equal concentrations of the weak acid and equal concentrations of the weak base in the mixture. What would happen to the pH when we do the following? So if I add acid, what's going to happen to the pH? Is it going to become more acidic or is it going to become more basic? It'll become more acidic. What about if I add conjugate base?
pH will go up.
Yep. Now what if I add strong acid?
It'll stay the same.
It's not going to stay the same.
Then it'll go up.
Pardon?
Then the pH will go down. The acidity will go up.
Correct. What if I had strong base? Increase in pH. So how does that feel? Like fun?
Yeah.
Keep her moving. Well, it doesn't work. It doesn't work. I tried. Doesn't work.
What doesn't work?
That made me sad.
Made me sad too. All right, now, this question is asking, again, equal concentrations of CH3, of the acetic acid and the acetate ion. what will be the majority species in the above system? So by majority species, and I know that species is usually reserved for biology people, but in chemistry, chemists generally refer to the reactants and the products as species. So there are 4 species in this particular equilibrium reaction. And so when I say the majority species, I'm asking which one of these concentrations will be the greatest after this has happened. So A, nothing has been added. Will be the majority species. Don't overthink it.
Water count.
No.
Okay.
In this case, because they're equal in concentrations, there will be no majority species. Okay? Now, what if I add some acetate, or some acetic acid rather?
Acetic acid. Or no. Yeah. It'll be the conjugate base.
So that's gonna go up, and the hydronium will go up as well. What if I add the acetate ion?
Acetic acid. Water doesn't count. Or does water count?
No.
No, so it's the same as-
So what if I had strong acid?
The acetic acid.
Well, I'm adding acid, right? Remember when I add acid, this is what happens.
So each reacts with the acetate to form our acetate.
Yeah. That's.
So in this case, we said in the last slide that when you add strong acid, it becomes more acidic, yeah? And and we said that the pH will go down?
Yeah.
So what has to go up in order for the pH to go down? The H3O plus. So in this case, when you add this strong acid, right, we're gonna increase, there'll be an increase in because it's gonna react with the acetate ion, so there'll be,
So that and H3O plus. Okay, that's what.
okay?
Wait, how?
So the H plus is gonna react with the acetate ion, and when it reacts with the acetate concentration is gonna go down. The H3O plus is technically gonna stay the same, but we're going to increase the acetic acid because that H plus is going to create more acetic acid, making it a little bit more, making that be more than the majority.
Why would it do that instead of making H3O? I mean, couldn't it do both?
Well, the issue is that it's not really gonna do both because it's gonna react with the conjugate base, and the H3O plus is gonna stay the same. So the H3O plus is going to stay the same, and as a result of the H3O plus staying the same, the pH goes down because the acetate ion concentration goes down. And then the NaOH, what'll happen? Just remember, it's a strong base, so, whoa. So NaOH will react to form Na plus and OH minus. So what's gonna happen here?
H3CO minus concentration will increase.
Like that. So we go to that. All right, so now we need to get to math. Ready? Moving on? Keep her moving? So buffers resist pH changes when strong acid or strong bases are added. So here's our acetic acid acetate buffer. We talked about Le Chatelier's principle, buffers being resistant to large changes in pH. So conceptually, if we add a strong acid, it will react. There'll be more collisions with the acetate ion and the H3O plus. More acetic acid will form, and the pH will be relatively stable. When the acetate has been all used up, though, the acetate ion has been all used up. The pH will drop drastically due to the large excess of H3O plus ions, okay? And conversely, if we add a strong base, the strong base will react with the H3O plus in the system, so more acetate ion and H3O plus will need to be formed to restore equilibrium, and as a result of that, the pH will be relatively stable. Eventually, all of the acetic acid will be used up, and the pH will rise drastically due to the excessive OH ions from the strong base. So this is getting at the fact that no, a pH or a buffer system can't go on indefinitely. At some point, it's going to be, you're going to use up one of the things, and when that happens, you're going to go into an alkaline, which is basic, or an acidic situation. The trick is to know about when that's going to happen. But that's, I think, another scope for another class. So, moving forward.
You said it will either be acidic or basic once the buffer system works. How do you control
What now?
it? After the buffer system is done?
It depends what you're adding. So if you're adding a lot of strong acid, it becomes acidic. If you're adding a lot of strong base, it becomes basic.
Like you.
What?
It's the
Okay.
It's Friday, you guys.
So the first row here is an unbuffered solution. And I'm telling you it has a pH of 5, okay? Now, if I add, in this, I don't know if you can read it on your slides, this is 1 milliliter of 1 molar HCl. If I add 1 milliliter or 1 molar HCl to an unbuffered solution, it drops drastically to a pH of 2.
Only
what
one
does that
milliliter?
say? What does that say?
1 milliliter of 1 molar.
Yes, it says 1 milliliter
Oh,
of 1 molar HCl. Okay? If I add 1 milliliter of 1 molar NaOH, the unbuffered pH solution with a pH of 5 jumps up to 12.
that's crazy.
It is. Now in the buffered solution, we have a pH of 5. And so if I add again 1 milliliter of 1 molar HCl, the pH only drops by 0.02. And if I add 1 milliliter of 1 molar NaOH, the pH only increases by 0.02. So buffered solutions work pretty well, even when you're talking about adding strong strong acids or strong bases. So what that tells us is that when we have to figure out how to make a buffer, there are some things that we need to consider. Moving on. It can be. So this slide is all about the derivation of how we get from the Ka expression to something that we call the Henderson-Hasselbalch equation.
That's a great name.
Well, it's a two human situation. It's not,
That's a really good name.
it's not one human, it's
Yeah.
two.
No, but it's a
Let the
good
Daniel
name for.
Hasselhoff
Don't do that.
Name.
Now,
Well, if it helps them remember it.
Henderson-Hasselbalch basically says that the pH will be equal to the pKa when you take the log of the concentration of the conjugate base divided by the concentration of the acid, at equilibrium, okay? So they have to be the equilibrium concentrations. Now, do you need to know how to derive this? No. Do you need to know how to use this formula? Yes. Will it be something you have to memorize? No. The College Board gives you this formula on the back of your periodic table.
Oh, hell yes.
Okay? Somebody last unit tried to use this formula and almost got it right. Almost got it right. Almost got something right. They just screwed up the concentrations.
We almost got something right.
They grabbed the wrong formula, but they almost got it right. It would have worked. Can I move on?
Yeah.
That in a minute. So we should have a little bit of understanding what the Henderson-Hasselbalch equation does for us conceptually. So I don't know how often they're going to make you calculate the Henderson-Hasselbalch equation or on the multiple choice section of the exam, but I think you should have at least an understanding. So if by chance the concentrations of the base, the conjugate base, and the weak acid are equal at equilibrium, right? So if it's 1/1 or 5/5 or 0.002/0.002, you get log of 1, and log of 1 has a value of what? 0. So by that definition, the pH will be equal to the pKa of a weak acid when they're equal. But if the concentration of the base is greater than the concentration of the acid, the ratio will be greater than 1, and if the ratio is greater than 1, when you take the log of a ratio that's greater than 1, you get a positive value, which means that the pH will be greater than the pKa. And if the concentration of the base is less than the concentration of the acid, the ratio will then be less than 1, and the log of a number less than 1 will have a negative value. And so the pH will be less than the pKa. All right. So when you have to actually make a buffer, or describe how to make a buffer, or have some understanding of how to make a buffer, you have to choose conjugate acid-base pairs so the pKa of the weak acid is close to the pH you want the solution to be stable at. What I mean by that is you want to be plus or minus 1 pH unit of the desired pH of the buffer. So if I want the buffer to be 8, I would pick the conjugate base acid-base pair so that the Ka of the weak acid is either going to be 7 or 9. Does that make sense? So if you had equal amounts of the weak acid at its conjugate base, it'll cause the pH to be the same as the weak acid. We just talked about that. And if you need to adjust the pH of your buffer solution, you would add amounts of acid or base to get to that right pH. You just add it dropwise. And remember that the conjugate base needs to be added as some type of a salt. So for the acetate ion, you could add any of those. And there's other options as well, but those are the ones I came up with off the top of my head. Questions about that? I'd probably steer clear of the calcium and the magnesium ones, but, you know, anywho. So we go to this. Questions about this? You should know that the 3 ways to make a buffer are the combination of weak acid and its conjugate base salt. You should know, you don't have this slide, sorry. You should know that the weak acid, that if you take a weak acid and a strong base, it will make a buffer. And you should know that the salt of a weak base and a strong acid will make a buffer. Do you need to copy all of this down? Probably not. You should probably know, though, the 1, the 2, and the 3. The stuff below is like the example. So weak acid would be, number 1's example is the acetic acid acetate buffer. Number 2's example is acetic acid and the strong base. And example number 3 is the acetate ion with hydrochloric acid. All of those make a buffer solution. Can I go on? People still writing?
Yeah.
Okay. I'm just trying to amuse myself back here.
Are we going to get through this?
We always get through it.
No, we don't. That's a lie, and you know it.
I don't know, but you weren't very specific. You said this, like, I
Are we
don't know.
going to get through?
Simmer
the
down.
lesson that you had planned?
Just simmer down. Simmer down now. Sorry, alive? No?
I get you, no worries. I have a father who watched a lot of it, so I know how it feels. You are the wild and crazy guys.
Can I go on now? Okay. In example number 3, okay, it says, given the data in the table below, choose a pair of chemicals, and what you've been given there is your acid, okay, that would allow you to make a buffer with a pH of 7.4. So if we remember that that in order to convert Ka to pKa, which is something that's helpful for us, the pKa is equal to the negative log of the Ka. Now, I was kind of nice, and I did a lot of the work for you, so we don't have to go through all the math here. But for the very, very first one, for chlorous acid, I determined that the pKa is equal to 1.96. 1.96. And I determined that the pKa of the lactic acid is equal to 3.86. And the that's PHA. That's silly. pKa of the hydrogen oxalate ion would be 4.19, and the pKa of the hydrogen sulfate ion would be 6.92, and the pKa of the ammonium ion would be 9.25. Okay, so those are our pKa's. So if we just decided that if we just said that the pKa should be within 1 plus or minus pH unit, which one of these would appear to be the best one? The hydrogen oxalate. So we would use something like the hydrogen oxalate ion, so like the HCO2C or O4 minus 1 with maybe H2CO4, perhaps? Or we maybe have NaHCO2C2. Wow, what am I doing? C2, hold on. C2O4. I don't know what happened over here. Hang on.
Yeah.
Not sure what happened over there. So what would the pH be when equal concentrations of each substance be? What's that? If I added equal concentrations, it would be 4.19. And how would we get this then to get to the 4.7? What would I have to add? Would I acid or base?
Acid.
I would, no, I'm trying to get to 4.7. All right, so, wait, here's the deal, ladies and gentlemen. This is a lot, and I am going to tell you that this is going to be due on Tuesday. Okay? So you should know how to do a lot of this already, but I'm not yet, but I have a couple of examples I have to do. So this isn't due on Monday, it's due on Tuesday, so I'm technically giving you 2 nights worth of homework, but you could start it now. But the vast majority of you are going to start it Sunday, no, wait, I lied, Monday night at 8:30, probably closer to 11:30, right? And as a result of that, it's gonna be a long night.